Chemical equations. So we can describe a chemical reaction using lots of words. That gets a bit tedious. And so we use chemical equations sort of as a shorthand. And they are similar to math equations. So here's an example of a chemical equation, and this is describing the combustion of methane. So on the left side, we have the reactants, the things that are reacting. So here's methane and oxygen. Those are reacting, and then the arrow says we're starting here and we're going over there. So the arrow indicates that we're going over here. This is what's being produced. We're producing carbon dioxide and water. These are the products. So the reactants react to produce the products. We're not trying to be tricky here. We're trying to be clear. But it just takes a little bit of working with these before you can really see what's going on. We often indicate the physical state of each of these things. So in parentheses here, the G means that this is in the gas state. And here O2 is in the gas state. And here the products are both in the gas states. We don't always include that, but sometimes we do. We include it when it's important, when it's needed, when there's question. Other times we'll leave it out. It really depends on whether we need it or not. So these are the abbreviations for the state symbols. G for gas, L for liquid, S for solid. Pretty straightforward. And then we have aqueous. Aqueous means it's a water solution. It's dissolved in water, and so we abbreviate that AQ. So, don't know what else to say about that one. So the chemical equation is describing what's happening. So here's that equation again. And here we have a representation of that in models. So CH4, here's the model. There's 4 hydrogens and 1 carbon. And O2 is a molecule containing 2 oxygen atoms. And then over here we have CO2, carbon with 2 oxygens, and we have water, H2O. So on the left side of the arrow, we've got 2 oxygen atoms, and over on the right we have 1, 2, 3 oxygen atoms. Well, we've talked about conservation of matter. You can't have atoms just appearing and disappearing. You can't create atoms out of nothing, and you can't just destroy atoms. So what do? Well, obviously there's something wrong with our equation. Our description of what's happening is incorrect. If we look at hydrogens, we also have a problem there, because here there's 4 hydrogen atoms, and over here there's 2 hydrogen atoms. So a creative person might say, well, maybe those 2 hydrogen atoms that seem to disappear, maybe they got changed into the oxygen atom. No. Good try for creativity, but things like that can only happen in nuclear reactions, and we're not talking about those yet. Okay, chemical reactions, the atoms stay the same. It's a lot like building with Legos. You can imagine, and we have model kits like this, and if you want to play with one, I'll be happy to pull them out. In this reaction, you have 4 of these little white balls, and they're stuck onto the black carbon. And when the reaction occurs, it's just like taking the model apart, taking the building blocks apart and putting them together in a new way. You don't have Legos appear and disappear while you're building with them. They don't just morph into other things. So we have to fix this description so that we have the same number. We need to balance the equation. So we can fix the oxygen by putting a 2 here. If we start with 4 oxygens and we end up with, well, that's 4 oxygen atoms. So 2 oxygen molecules would give us 4 of the red balls. And then over here, if we put a 2 in front of H2O, now we've got 2 red balls there and 2 red balls there. We have 4 oxygens on each side. And that also took care of our hydrogen problem, because now we have 4 hydrogen atoms over here, and we started with 4 hydrogen atoms. So you can imagine taking these three little models, taking them apart and putting them back together, and you can make those three without any extra pieces, without having to borrow from somebody. Does that make sense? That is all a chemical equation is doing, is describing what's going on here. So to balance this, we put a coefficient, a number in front of the oxygen, because we can say, well, we need 2 oxygens. We can't say, well, we need half of an oxygen molecule, because you can't have half of a molecule. So we can only add more of them. So we put a 2 in here, and we also can't change the formula. We can't say, well, it must be O3. That would balance it, because it's not O3. O3 is ozone, and it's not ozone, it's oxygen here. So you can't change, you can't touch those subscripts. It's a tempting thing. It seems easier, but you can't do it. You just put a coefficient. So this means 2 oxygen molecules. 1, 2. And the 2 over here means 2 water molecules. Okay?